All right, it's my great pleasure to welcome Marius Zeinhofer from Simula today to this One World seminar on the mathematics of machine learning. And he is going to present work on the error analysis and optimization methods for scientific machine learning. And well, without further ado, floor is yours.
Thank you so much, Stefan, for the introduction. And thank you to the organizers for giving me the opportunity to speak here. So today, my talk will consist of two parts. And I will start with an error analysis for physics-informed neural networks, or short PINs, where I'll focus on a framework for the analysis of linear PDEs. And we're going to derive a priori and a posteriori estimates and have a look at the influence of hard-coded constraints, meaning boundary constraints that are exactly enforced in the ansatz, or divergence constraints or initial constraints. In the second part of the talk, we'll change gears a little bit and we will be looking at optimization methods, not only for physics-informed neural networks, but also generally for problems in scientific machine learning. And when I say scientific machine learning for this talk, I mean I collect methods like neural operators, physics-informed neural networks, the rational Monte Carlo with neural network ansatz functions all together in that name. And we will focus on second-order methods that are motivated by function space methods and design them in a way that they mimic the function space dynamics. And we'll see that recently proposed methods that are very effective for these kind of problems can be understood from this viewpoint. And this will yield us a guide for the design of new algorithms. So let's jump into the first part. I'll give a brief introduction to the concepts of physics-informed neural networks. And I will do that with the example of Poisson's equation, although it is understood that you can choose virtually any PDE. So let's say we have a domain omega that sits in RD in the physical space, and we want to solve Poisson's equation for given forcing data and given boundary data G. So very naively or straightforward, you can say solving these equations under the right assumptions on the forcing and the domain and the boundary values is equivalent to minimizing a functional E on in this case, the Sobolev space H2, where you penalize both contributions on the interior from the PDE and the boundary values. And also already here, I want to stress that associated to this energy E, we have the bilinear form lowercase a. You can get it as the second derivative of that E, or you just see it. And this is a quadratic problem. And it's given by the contribution of the Laplace operator and the contribution of the boundary term. So this form A will be important later in the analysis, because the properties of A will almost completely determine the analysis, at least one part of it. And to have in mind that we're not only interested in the Poisson's equation, you can just replace the Laplace operator by virtually any linear PDE operator here. And likewise on the boundary, you could replace this by a boundary operator when, say, you're interested in a Neumann type boundary condition or Aubin type boundary condition. So this is really to be understood as a placeholder for general linear PDEs. And the next step is the discretization. And in this case, it's a discretization with neural network type ansatz functions. I will not make the neural network ansatz explicit. I will leave it as a parameterized ansatz that lives inside this H2 space in this case. This capital theta is the parameter space, lowercase theta are the trainable weights, and u theta is the function represented by a neural network. And then what is done is in practice is to solve a minimization problem over the trainable parameters. And here I introduce L for the loss function, and the loss function L is approximately E, which was the optimization, the minimization formulation of the PDE, and it's approximately L because we need to discretize integrals. And this is made concrete here, where L is approximated, where the integrals are approximated in this case, maybe by a Monte Carlo type of approximation, maybe by a quadrature rule. It depends on it depends on your choice, on the application also. And then it is important when you're solving this problem and when you're minimizing L, that after your optimizer of choice, you end up with theta star and also corresponding a function u theta star. And you cannot assume in practice that that lowercase theta star is actually the solution of this minimization problem. Rather, you get a quasi-optimizer. So this is important to realize in the error analysis later, that we cannot assume that we're solving this problem, but maybe we're getting close. And then the error we care about is the error in function space. So u star, which is this true underlying solution, the ground truth, minus the function represented by theta star. So this is what we're caring about. But here, this guy does not have any Galerkin orthogonality that it satisfies or anything. It's really just a quasi-optimizer. And then I want to comment on what has been done in this direction, because there are several results on the error analysis. And the results that are out there in the literature, I've listed two of the most cited works here. They are typically of an a posteriori type, controlling the L2 norm. So this is the error. This is what we care about. The results in the literature control this term here. But there is a drawback that in this analysis, in these papers, the constant depends on u theta star, and it can depend on the C2 norm of this u theta star. And then here you have you have the loss, or in this case, the continuous version. So it's not ideal to have these constants depend on u theta star. You rather want them to be independent. There's also no a priori component in the analysis. The analysis assumes the existence of C2 solutions. So what we set out to do is to derive a priori and a posteriori estimates under more realistic smoothness assumptions, where I'm referring to C2 here. We will focus on H2 solutions, typically, which is weaker, and remove the dependence on u theta star here in these constants. So let's get into the framework, the abstract framework that we have to analyze these type of problems. And if you remember in the introduction with the Poisson equation, I mentioned the form A, that was a bilinear form that had a Laplacian here instead of L, and which had just the Dirichlet boundary value from the trace. So assume we are given an A, which is of this form. You can also include time dependence here in this operator if you wish. And then the crucial ingredients for an error analysis, and this is exactly the same as in finite element world, are these two conditions on the form A. You need a coercivity, which just means that this inequality, this lower bound on the form A holds for all u in your Hilbert space H. And you need continuity, so that's an upper bound. It looks like this. And note that I put here a triple norm instead of the normal Hilbert space norm H. This norm, for example, would be H2 for Poisson, but we will see that in the formulations that is typical in pins, we are not able to choose these two norms the same, and instead we must resort to a weaker norm. So this explains this triple here. And under the assumption of coercivity, we'll immediately get a posteriori error control, an estimate of this type. Again, this is the error. This is what we're caring for. And then we can control it with the loss, but E, remember, E is the integrals are not discretized. So we get a control of that error in terms of an almost computable quantity. And here I expanded E into L, which is really the loss when you discretize the integrals, and the error in quadrature that you make. So what this result means for you is if you want to control your error, and you are willing to maybe spend more computational resources on quadrature, then you can do that, and you will get in control, which is maybe tighter. You are able maybe to reduce this quadrature error. I'll comment more on how to control this quadrature error also later. And then we also have an a priori error control. Now we assume that the form A is both coercive and continuous. Then we can estimate, again, this is the error, this is what we're caring about. We can estimate that as a sum of two contributions. Let's look at both terms. So the last term is what is typically called a best approximation. So this is really a question of estimating this last term is a question of approximation theory, where u star is your underlying solution, and u psi now goes through all your neural networks in your ansatz class. So this term you can treat with quantitative universal approximation theorems. This delta term.
Marius, can I briefly interrupt you? Can you say a few more words about the triple bar norm? There's a question in the chat.
Yes. So probably this will also become clearer when I look at this on a concrete equation. Maybe it's helpful to think that math-cal H is the space on which it makes sense to formulate the Poisson equation. Say math-cal H is H2. So this norm is H2. And we will see later that in the example of Poisson's equation, the best you can hope for here in the Sobolev regime is H1/2 on omega. So this is a weaker norm than this norm. The triple norm is weaker than the H norm. If it stays unclear later in the examples, please interrupt me again. Or if it's not, yeah. Okay. So this is approximation, and then there's delta, and delta quantifies the mismatch between the infimum of E over the ansatz class and what you're actually getting after optimization. So on the maybe before I will go into a little bit more detail about the infimum term and delta 2, but before I do that, maybe 2 words on the proof of this lemma. Lemmas like this, CS lemma, are well known in the numerical analysis community. There are two ways in which this lemma differs from the existing literature. One is that you cannot assume that this delta is 0 for finite elements. You would know that this is 0, that you're exactly solving on your linear ansatz class. And the other thing is about the proof. You cannot prove this with using the tools of Galerkin orthogonality, because this u theta star, you do not know that it solves any optimization problem. So there will be no optimality condition. That being said, I'll proceed first with an explanation of this delta and how to further estimate it. So this delta term, I will now further estimate it, and you can decompose it into a global discretization error and an optimization error. So the global discretization error is this here. E and L, they differ only in the discretization of the integrals. You're here taking a supremum over the whole ansatz class. And the second term is really the optimization error. How well are we able to solve the minimization problem? Now, in some cases, these two quantities can be estimated further. For the first, for example, in the case of Monte Carlo integration, Rademacher complexity would be an appropriate tool to control this contribution. And I've listed one of several references where this is done, for example, for the Poisson equation. And the second term, in case you are using a greedy algorithm to solve a problem like this and your ansatz class are shallow neural networks, there are guarantees by work of Jonathan Siegel and co-workers that are able to estimate this term. But both admittedly are not the full generality. So the story is not finished here, these estimations, but there are first positive results. And then let's look at this infimum term. And then it depends on what kind of norms you want to estimate this. So typically there will be Sobolev norms that you need to control. They are dictated by the nature of the PDE. So the PDE just lets you do what you can do with it, and you will typically end up with an infimum over a Sobolev norm. And there are results in the literature that tell you what kind of rates you can expect and how many degrees of freedom you would need to use, for example, in this paper by Güring and Rassler. For shallow neural networks, for example, you could also be in the favorable situation that your true solution has barren regularity. And then you might be able to derive a dimension-independent estimate here. And there are, for example, the results here by Siegel and Jin Zhao in this direction. But this is just to mention what there is, and what I will be focusing on most now is actually the coercivity estimates for physics-informed neural networks for these types of formulation. Here's a brief summary of the estimates we have. We have a posteriori error control with the continuous integrals. We have it with a quadrature rule if you assume that we have a rate for the quadrature. We have a priori estimates with the approximation term. And we have some estimate on delta. So this whole box here just follows from continuity and coercivity. So these two properties are crucial. And that's what I want to discuss now for a number of equations. And to this end, let's get back to Poisson's equation again as a model problem. And actually the strategy to derive these estimates will work for a large class of linear equations. So let's get back to this formulation, E. The corresponding form is this here. We've seen it before in the talk. And then we're posing the question of, especially of coercivity estimates. Continuity estimates are typically easy. So let's focus on coercivity. And you can immediately observe that regularity estimates, which would be maybe a canonical tool here, they will not just do the trick, because you're penalizing L2 here on the boundary. And if you were to use regularity estimates, the natural norm would be H3/2. And this is the same for initial and divergent constraints. These are all always done in practice in L2 norm. So you need to do something else to provide these results here. And because they are prevalent in practice, these L2 type penalizations, that's what we're going to be analyzing. And we have a general strategy to get these results. Consists of 3 steps. The first step is to derive energy estimates with inhomogeneous data. So energy estimates are actually estimates for the H1 norm for the energy spaces. And then the step 2 is we assume smooth enough solutions, say H2 regularity. Then we can derive dual estimates, estimating the L2 norm typically, the error. And then in the third step, we will interpolate, use result from interpolation theory to interpolate between the results obtained in step 1 and step 2. Let's exercise this on Poisson's equation. So energy estimates look like this. We control the H1 norm by the dual norm of the Laplacian and the H1 norm on the boundary. This is standard application of Lex-Milgrom. Then we derive a dual estimate. Here we assume that U has H2 regularity, so that the problem itself has H2 regularity. And then we're able to control the L2 norm of U in terms of the Laplacian in the dual of H2 and in the dual of H1/2 on the boundary. And this typically works by considering a dual problem, integrating by parts, and then estimating. And in a third step, we just interpolate between these two estimates. And then we're getting H1/2 here. And this will actually be, this is in this case, in this example, this is the triple norm, H1/2. And we can go up to the interpolation space between these two, which happens to be H3/2, H10 intersected dual. And it happens to be exactly L2 on the boundary. And then we say, okay, we are generous, and we go up to L2 here, and then we recover our form. So in this way, you can get the coercivity. And this proof strategy, luckily, works for quite a number of linear PDEs. So we've done this for elasticity, for Darcy's equation, where for the flux and pressure you get different spaces. Now here you get the Lyons-Marguenes space, which just appears naturally as an interpolation space. For parabolic equations, you get L2 with values in H1/2. For hyperbolic, you get more complicated spaces. These stem from the exponents. They just they come from interpolation and the natural norms for the boundary and initial conditions. For Stokes equations here, and you always see this mismatch. Continuity needs to be measured in to be in a stronger norm than coercivity, and the norm where you have coercivity, and that is the norm with which your error will decay. So in all these examples, you see that the error decays in a weak norm, but you need a universal approximation for these spaces. And lastly, I want to comment on how imposing certain conditions like boundary conditions or divergence conditions exactly in the ansatz space, how this will improve the mode of convergence. And let's do this with a stationary Stokes system. So we have a pair of velocity and pressure, and we assume that our ansatz does not satisfy any constraints. And constraints in this case are divergence constraints and boundary values, Dirichlet boundary values. And then on the previous slide, if you believe me, the error decay, so the coercivity will only hold in this norm. So you have H1/2, because on the velocity you have an elliptic and Laplace term, so you have H1/2 here too. And the pressure will only be converge in H1/2 in the mean value free H1/2 functions, but then you have a dual norm here, so just in a weak norm. If you decide, now with this here, I mean that your ansatz class exactly satisfies the boundary conditions, which you can do if you design your ansatz smartly, then you can improve your coercivity to H1 and L2. And this makes sense because then the penalization on the boundary, which should have been H3/2 for a strong formulation, now just is exactly satisfied. So you're not polluting your coercivity with that, but you're polluting your coercivity because you penalize the divergence in L2. But in a strong formulation, you should be penalizing divergence in H1. So this is why we get So we're sort of one smoothness away from doing the right thing in divergence. So we get H1 and L2. If you happen to have an ansatz that is solenoidal and also satisfies the boundary conditions, then you get error decay and coercivity in the natural norms of the strong formulation. So we thought that this is an interesting observation and also interesting to quantify this, because it is also observed in practice that encoding these constraints helps the training. So with that, I'll end the part on the error analysis and move forward to optimization methods, now changing gears away from pins to more general problems. But maybe if there are questions concerning the error analysis, this might be a good time to ask them.
Can I ask a question? If you so you have these error estimates, does that give you any insight into how to say design a pin functional? Because obviously you can penalize the mismatch in L2, which is the common way, but you could also say penalize the mismatch between the PDE and the effective output in a stronger norm like H1. So you get any insight into how it would be, what would be a good idea to design your loss function?
You definitely get some insight. So for example, let's take this middle bullet point. Here I said, and let me parse this for you again. Here I say, okay, we assume that this is a Stokes problem, and the Dirichlet boundary condition on the velocity, we have them exactly. Well, let's agree on that. And then if you were to penalize your divergence in H1 instead of L2, then you would get H2 and the gradient seminorm also here, because then you could just apply the natural regularity estimates for Stokes if you so happen to be in a setting where you can apply them, right? And this is in all this analysis, you need to be in H2 regular setting for this analysis to work. So definitely, yes, you get some leads on what on how it should look. Sometimes, for example, then you could say, yes, you should maybe penalize boundary values in H3 halves, but this might not be so easy in practice to implement. So sometimes it will give you maybe things that you should implement and try out, and sometimes not. But of course, there's also the question of will the solver actually reflect what this analysis says? So with a linear ansatz space, I'm very confident that you would see this. And with a nonlinear ansatz space, it might be difficult to actually see this in practice. So these are two things to keep in mind.
Thank you.
May I make ask a question and comments?
Sure.
Your analysis apparently show that this square functional is not right functional for the problems, right? You mentioned that first of all you need H2 functions, and also you need you lose the balance between the coercivities and the continuities because of the bad treatment of the boundary conditions. You know exactly it should be 3/2, right?
Yes, that's exactly true. I mean, it is maybe not the wrong functional in a sense that it gives you a wrong solution, but you're sacrificing convergence mode.
You lost the opportunity.
You are still converging in H1 half to the right solution. So you're still approximating the right solution with this formulation, but you are maybe not approximating it with H2.
You lost a lot of optimality in the computation, and also you lose the stabilities in the. I just make a simple comment. Is the if you're looking at this as original least square functional, actually Bramble and Schartz in 1971. Well, you already know that result is the boundary condition should be 3.5. After that, there are a lot of work on the least square functionals. What is the right for each PDEs? what is the right D-square functionals. There are many work of that. So just make a comment of it.
Yes. Thank you. Yes, and I mean, just to comment briefly on your comment, you could, of course, and to my knowledge, the least squares community, finite element community, prefers, of course, reformulations in terms of first order systems.
Yes, that's what
this might also be, from a theoretical standpoint, certainly more correct also in these type of formulations, also with nonlinear ansatz spaces.
Yes, we do that. That's what we do. Yeah. Thank you.
Yeah. Thank you too. So if there are no further questions, I might move on into optimization.
Maybe one more question regarding this. So if you would, I think it's very related, but if you would, for example, take the Debritz formulation for this kind of Poisson equations, I guess your analysis would still be applicable, but what would change?
Thanks for the question, Julius. If you use Debritz, then you are actually using sort of the right norms. So then you would get, then you would not have the mismatch in coercivity and continuity. These two would be the same. There might be a question on how you enforce boundary values. So if you want essential boundary values, then you need to resort maybe to the boundary penalty method or to Nietzsche's method. If you use boundary penalty, you're making a model error. You're solving a Robin problem instead. So you make an error with a boundary penalty parameter. So you might use Nietzsche's method. So in that sense, it would be more correct. I think what is observed in practice is that Debritz is more difficult to make work in practice, and I believe that this is due to problems in the quadrature error. But this is me claiming it right now. Maybe we can talk about this offline or after the talk if you're interested. So I think Debritz suffers from quadrature.
May I make a comment?
Yeah, sure.
For the Ritz, now instead of the 3/2 norm, you should have a half norm. Then that everything is balanced.
Yes.
This square and the Ritz, both formulation have a problem with the quadrature, because where to choose the quadrature point depends on the problems, depends on the local phenomenon of the problems. The standard Monte Carlo is not a very good approach.
Yeah, I think there's even a bigger problem. There's even a bigger problem with the quadrature in Debritz, but maybe we can take this after the talk.
Sure.
Sounds good. Thanks a lot.
Thank you for the question. Then I think I'll move on. And then just to reiterate, now I want to change gears a little bit away from pins only to general methods that involve neural networks and PDEs. So for instance, operator learning, irrational Monte Carlo for many electron Schrödinger's equation with neural network ansatz functions, but also including pins, Debritz methods, so anything that involves PDEs and neural networks. And I claim that introducing PDEs into PDE terms into these objective functions will complicate the neural network training drastically. And to substantiate this claim, I have here two pictures. One is from the paper of Li et al., the forward Laplacian paper, which recently is a preprint at this stage, I think, where the goal is to solve many electron Schrödinger's equation, in this case for naphthalene. And why I took this picture is the number of GPU hours for a single run. So they're spending thousands of GPU hours. And this is also a high-dimensional problem, so it's a very difficult problem. But certainly contributions to optimization will be meaningful in this field when you're willing to spend this much. And this is a picture of a paper by Johannes Müller and me, where we tried, this is a very simple problem, it's just a Poisson problem, where you see that if you use the pin formulation and a first order optimizer, the red curve, in this case is Adam, and the green curve is gradient descent, they will take a lot of iterations and then also not reach high accuracy. So what I propose for this talk, or as a general discussion point, is maybe one should try to abandon first order optimization for these type of problems. And instead one should look to exploit the geometry that is induced by PDE operators. So what I propose, how one should look or consider looking at these problems is, say we are given a SciML problem. So it's optimizing a nonlinear ansatz class and a network ansatz class, and the loss function involves PDEs. So the first step I say is we should formulate this as a problem in infinite dimensions. So you have a functional E is defined on a Hilbert space, goes to the reals, and you want to minimize E. Second step is that you decide for an iterative, typically or I know only of iterative algorithms, you decide for an iterative algorithm. So you update, you start with U0, you update UK plus a direction dk, and I introduced here a step size eta k also. And you choose that minimization scheme here. You choose it depending on the properties of E. So you look at E, you look what is the structure of E, and then you choose your minimization algorithm. And then in the last stage, you discretize this algorithm, and I will make this concrete on the next slides. And what the goal is, that the update should be a projection of this dk guy, of this function space guy, on the tangent space of your neural network ansatz class. So your goal is to follow this scheme here. And let's make this concrete again with a simple problem. The problem now will again be from the pin type of formulations, but it's not tied to these problems. So we want again solve Poisson's equation. We reformulate this as a minimization problem. So this was here before. This is a problem on a Hilbert space. The Hilbert space in this case is H2. But of course, there's nothing that forces us to formulate it exactly in this way. We could formulate it as a root finding problem for the systems of equations. We could formulate it as a saddle point formulation, but okay, we'll formulate it as a minimization problem in this example now. And for now, we ignore neural network ansatz classes. So this is our infinite dimensional problem formulation, the first step. The second step is that we look at E and ask ourselves, what are the properties of E? And E is a quadratic functional. So we say, okay, Newton's method has one-step convergence on quadratic functionals. Newton's method in function space. And if I write out Newton's method in function space, it looks like this: second derivative inverted applied to the first derivative. So this guy is the update direction. And I ignored here that if I put U0, that this is U star after one step. This is true for quadratic, but I need this formulation to discretize it in a second. And in general, this is what I mean when I say we choose an appropriate optimizer. Here quadratic and then Newton with one-step convergence is of course very appropriate. And we still ignore the neural network ansatz classes. And then the third step is we do a Galerkin discretization in the tangent space. So now we introduce our ansatz. Now we introduce the neural network class, M. Now we also introduce the tangent space, and the tangent space consists of the partial derivatives of the neural networks with respect to the trainable weights. And there's no reason that these guys need to be linearly independent. So it's not a tangent space in the strict differential geometric sense, but nevertheless, I call it a tangent space. And then I call L now the loss function is just the continuous function evaluated at the network that has these parameters theta. So we forget about integral discretization in this part of the talk. And now we discretize Newton's method with a Galerkin ansatz in the tangent vector space, in this vector space. So the second derivative is a bilinear form, and this will give us a matrix, which I call G, referred to sometimes as the Gramian. And you get it via inserting the partial derivatives, these partial derivatives here, into the second Fréchet derivative of the continuous guy. And derivative you discretize also with the Galerkin ansatz, so you just put in these guys in the Fréchet derivative, and what you get back is the Euclidean gradient of the loss, so what you would get from autodiff. And then after discretization, you just write down what you got. Now you get something computable in parameter space. So your parameters are updated by inverting. I need to put pseudo inverse here because these are not linearly independent. Pseudo inverse applied to the gradient of the loss. So this is the algorithm. And if we do that on the concrete example I had on the slides earlier, then this is how the matrix G looks for the Poisson equation Laplace applied to the partial derivatives of the neural network ansatz, and also the boundary terms. And if we do that for this example, we get a highly effective algorithm. We get this blue curve here. We can solve Poisson's equation in the pin formulation with just a handful of iterations. And it's better than BFGS Adam gradient descent. And I'll exercise this a little bit faster again, just to illustrate the point that there is flexibility. And let's say maybe our problem is not a linear PDE, maybe it's the Navier-Stokes equations. Look like this, it's a nonlinear PDE. And again, we formulate it as a minimization problem. Again, I choose the pin formulation. And here I assume that my ansatz is solenoidal and respects the boundary values for simplicity in the presentation and the formulas. But you could also do the full penalty here. And then my E looks like this. And then the question is, okay, we still ignore the network ansatzes again. Then the question is, what properties does this E have, and what is an appropriate optimizer on the function space level? And then I look at it, and then I see, okay, this is a nonlinear least squares problem. And then I might choose Gauss-Newton's method in function space as a method for a nonlinear least squares problem. And if I choose Gauss-Newton's method in function space, this is what the algorithm looks like. You linearize the nonlinear residual. You get back a quadratic model. You solve explicitly that you minimize explicitly that quadratic model, and this is what you get back if you do the computations. And then looking at this guy here, you see that it's again a quadratic form. So you can discretize it in the same way as you did with the second derivative before. Again, we discretize U theta, P theta, both velocity and pressure with neural networks or anything parametric. The tension space, again, is the same, consists of these partial derivatives. And then we discretize Gauss-Newton using a Galerkin ansatz in the tension space. And we get back a matrix that you get by inserting these partial derivatives into this guy here. And again, we get back an optimization algorithm that looks exactly the same, only that this G now has this definition. And again, we get a highly effective algorithm. So here the example is for an unsteady 3D Beltrami flow, which is a typical benchmark problem in Navier-Stokes. And here we have Adam, BFGS, and what I just showed you, and the discretization of Gauss-Newton's method in function space. So in both cases, we get back something effective.
Can I ask a very quick question?
Sure.
Your graphs have in terms of iterations, but then to compute your step size, you need to do many things. So each iteration of your algorithm takes much longer than just standard. Do you have a comparison in terms of either operations or runtime or something like that?
I don't have it here on the slides. I have it in one of the papers I can share with you, but this question is very valid. And I can also just say to you that I don't have a very good or general answer to this question right now. Of course, these are second order methods, and they don't have a favorable scaling with the size of the parameter space. You have a quadratic memory requirement for the matrix, and you have a cubic requirement for the matrix solve, the cubic complexity for the matrix solve. So it depends very much on how big your parameter space is, if you actually save time or if you lose time. So the selling point in this situation is that you are actually able to achieve good accuracy in these type of problems, something that you could never achieve, say, with Adam. And then the question of runtimes is, I think, further down the road. Maybe I'll talk a little bit more about scalability very briefly, and maybe you ask me again, or maybe, right? But it's a very valid point. Will this be faster in the end if done right? It's a good question.
Can you make a comment about how
Thank you very much.
Can you make a comment how to invert the pseudo inverse?
Yes, I can make this comment now. We have two methods. One is you assemble the matrix and you use an SVD-based solve because it can be singular. Or if you happen to add a little bit of an identity as a stability on your matrix, you might be able to do a Cholesky decomposition. Or the other way that scales to larger networks is to use a matrix-free implementation, where you only compute the application of that matrix on a vector and you resort to, say, a CG to solve the problem. I'll comment a little bit on this also later. Maybe one slide on further examples, where now I've showed you Newton and function space and I discretized it. And then I showed you Gauss-Newton and function space and I discretized it. And there are also methods that are currently out there in the literature. For example, for versional Monte Carlo with neural network ansatz functions, K-FAC actually is nothing but an L2 gradient flow on the Rayleigh quotient. So what is best practice right now in these methods can actually be understood from this function space viewpoint. And then there's also recent work by a group at Georgia Tech on a reformulation of pins in terms of a saddle point problem, where they use CGD, so competitive gradient descent, which is a second order method to solve that saddle point problem. And you can actually understand the application of CGD to the saddle point problem. You can understand that as a Lagrange-Newton method. So Lagrange-Newton is, you have optimization on the equality constraints. You do a Lagrange multiplier formulation, and then you use Newton's method to solve the optimality condition. And so you can see that these two things are the same, so that the infinite dimensional viewpoint also gives you insight on what there's actually doing. So here I have a list of situations where I know that this is the case. So gradient descent in a Hilbert space, this is L2 gradient flow, for instance, is typically referred to as a natural gradient method. Newton is what I showed you. What I didn't say so far is that if you discretize Newton, you actually end up with a known method. It's the generalized Gauss-Newton's method. And this is a recent paper also where we comment on this in detail. This I said, Lagrange-Newton corresponds to CGD. It's introduced as C-pins in the literature. This holds for linear PDEs. If you use Gauss-Newton in function space, you actually get back Gauss-Newton in parameter space. So these two are the same. And this was what I showed you for the Navier-Stokes equations. And then maybe some words on theory behind it before I get into a little bit into scalability questions. This is about, can we say something between the connection of the method in parameter space that you're getting after discretization and the continuous method? How do they align? So what I showed you so far is typically of this form. on function space. So you have the Fréchet derivative. This is something you can compute by hand. And then you have a linear map that goes from the Hilbert space to its dual that you need to invert. Depends on where your iterate is. So this is how your typical iteration looks, and this generalizes all of what I've shown you, or encompasses all of what I've shown you. Gradient descent, Newton, Gauss-Newton, Levenberg-Marquardt. And then if we assume that this map T here is coercive, then we have a theorem on what we're actually doing on the discretized level. So our discretized algorithms all looked like this. You update your parameters theta by a rule like this, where you invert this matrix here and apply it to the gradient. And under the assumption of coercivity on T, actually you can say that this is really the projection. This is a Galerkin projection of the function space direction onto the neural network tangent space. And this also, for example, generalizes natural gradient methods, which typically would require this T to be symmetric. You would say there's no need for symmetry. You need coercivity, and then you get a Galerkin projection. So it's still a quasi-best approximation. So you're following the function space dynamics. You have this projection that you do on the tangent space, and you have another error contribution, which is quadratic in the step size length that you choose, and also in the length of this guy here. The proof is just Taylor expansion and CS lemma essentially. So it's very simple. And here's a visualization of the projection theorem. This is again Newton's method on Poisson's equation with a simple solution. We initialize our network somewhere. So this is the continuous Newton step, and remember, the Newton step in function space gives you convergence in one step. So this you should do. And then if I plot the push forward of what the projected Newton gives us, these two align very beautifully. And if you visualize what the gradient tells you to do, this is clueless. And I like these pictures a lot. And to me, this is also, while coding, a good visualizing these things is always good to see if my method does the right thing. And then here maybe is the right time to comment on scalability questions. So of course, as already commented, you have a second order methods. Your matrices that you get, they are typically dense. So you cannot do this naively. And so far, strategies that I'm aware of is matrix-free approaches or KFAC, so Kronecker factorized approximate curvature, which approximates these matrices by Kronecker factors of smaller matrices. But both, you need to do this on a case-by-case basis. You choose an optimizer, you look at the properties of this specific discretization before you can get into this. And there are also many infinite dimension concepts that I'm very confident will translate, but that are unexplored. And an incomplete list is fixed point algorithms. I haven't started thinking about this. Trust region methods also. Operator preconditioning. Secant methods in function spaces. So I believe there's a lot of you can do with this framework and these ideas, and see what comes back, what you can do. I would also be interested in developing convergence theory that separates function space level and the parameter space. And with this, I'm at the end. So to sum up both parts of the talk, in the error analysis, we looked into a priori and a posteriori estimates for pins for linear equations, and saw that the crucial ingredients are coercivity estimates. And we also saw that we saw the impact of enforcing the constraints directly in the ansatz, or in other words, how L2 penalty can deteriorate your convergence mode. And in the second part, we had this framework for the discretization of infinite dimensional optimization algorithms. And I've listed 3 papers here that sort of have the essentials of this talk in them. There's this paper on the error analysis that contains mainly the coercivity estimates and also the abstract framework. Then on this paper here is on Newton in function space and the discretization. In this paper, it's introduced as a natural gradient method. We were not aware of the function space viewpoint when we wrote this paper. And then Reason just uploaded the other day here, and this is where Johannes and me summarize our viewpoint on this infinite dimensional optimization. So this is the last part of the talk. And with that, I thank you for your attention and happy to take questions.